Maxim, you should allow the sharing of the screen. It is.
Okay. Yes, that's right. Okay, now you should be able to.
Okay. Okay, so we are going to start looking at time series exercise. You should see the screen now. So if you remember, as we have seen in class, in this kind of exercise, we are observing sales of a company alpha, and our aim was that of estimating the forecasted value of sales for year 5, and in particular quarter 1 and 2 of year 5. To do that, we have first of all realized a graph. Remember that to realize the graph, you should select the column of your observation that is sales, click on insert. Excuse me, but I have the Italian Excel version in this computer. However, it is the same. So you should go on insert and click on line graph. Once you do that, you should end up with this kind of graph, and you should be able to interpret it. So first of all, in this case, we have quarterly data. So we are observing sales for year 1, 2, 3, and 4, and the respective quarters. So quarter 1, quarter 2, quarter 3, and quarter 4 for each year. So the periodicity of our data will be k equal to 4. So an even number. Remember this because it will be important when starting calculations. So once we look at the graph, we see that the series shows a linear trend. If you see, it is increasing, and a constant seasonality. Constant seasonality means that the peaks you observe always occur in the same manner as time goes on. Okay? So this graph should suggest that we need to apply an additive model in order to realize our forecasted value of sales. If you remember from theory, additive model implies that all the components of time series, that is the trend, the cycle, and the regular component and the seasonality, are related to each other by a sum. So they are just summed. So once we recognize this, we can start our calculations. And in this case, we are going to use all the formulas you have in the slides that relate to additive or linear model. They are synonymous, okay? So the first calculation we should realize is the estimate of the trend cycle component. If you remember, we have seen that the cycle component refers to fluctuations that the series has around the trend. And this component is difficult to estimate by itself. So we estimate it together with the trend by applying the moving average formula. What is moving average? First of all, remember we have quarterly data. So the periodicity of our data is equal to 4. And if you remember moving average, we know that in this case, we are going to lose k over 2 observations at the beginning and at the end of our time series. So given that k is equal to 4, we are going to lose what? 2 observations at the beginning, that are the red ones, and 2 observations at the end. So this means that we are going to start computing moving average from observation in line 4, this one, okay? What does it mean applying moving average? Essentially, we are going to replace the value of our observation by the average of itself and its k minus 1 neighbors on either side. Okay, so we are going to start using this observation, 495, and averaging this with the first two and the subsequent two observations. Remember that when you have a k that is even, the formula tells you that you have to weigh your observation using an alpha that assumes value equal to 1 for extreme observation, so the first and the last, and 2 for all the others. Then you should divide this for 2 over k, that is 2 times 4, in this case, since our k is 4. So we take the first observation times 1, plus the second times 2, plus the third times 2 again, the fourth times 2 again, and the last one times 1, divided by k. This will be the way in which you are going to obtain moving average value. And if you do just a double click here, you are able to obtain this calculation for the whole column in the same type. It is clear until now. You can write in the chat yes or not so that I know whether it's clear or not. Once we compute the trend cycle component, we should adjust our series for seasonality. If you remember, and again, seasonality refers to the behavior of these peaks over time, okay? To do that, since we are applying an additive or linear model, you know that we should compute the GSC, that is the gross seasonal coefficient. It's the difference between the observed value of sales and the value of the trend cycle computed by moving average. So the gross seasonal coefficient will be just the difference between the observed value of sales and the value you got before applying moving average to get the trend cycle. So just a simple difference, okay? Again, also in this case, if you click there, you double click there, you are able to obtain this calculation for the whole column. But besides the gross seasonal coefficient, we also need the net seasonal coefficient in order to account for the seasonality of our series. The calculations of the net seasonal coefficient seems complicated, but it is not. You should bear in mind that the net seasonal coefficient is just the average of the values of the gross seasonal coefficient for each quarter. So to make things easy, I have just created this table here. So you just have to divide first, second, third, and fourth quarter and report there the value of the gross seasonal coefficient for each quarter. So what does it mean? Let's start from the beginning. So we don't have a value of the gross seasonal coefficient for the first quarter of year 1, because remember, in this case, k is equal to 4, and we are going to lose the first 2 and the last 2 observations. So we don't have value for the gross seasonal coefficient for year 1, quarter 1. The first quarter available is that of year 2, quarter 1. So we are going to copy and paste the minus 56.5 in this column here. The other value will be that of 3.1, so year 3, quarter 1. The other value would be that of year 4, quarter 1. So in this case, you have just a copy and paste of this value in this column. You should realize the same for the second, the third, and the fourth quarter. So you are going just to copy and paste the value of the gross seasonal coefficient for all the second quarters of each year. So year 2.2, year 3.2, year 4.2 will end up there. The same thing for the third quarter. So we have year 1.3, year 2.3, and year 3.3. And the same thing for the fourth quarter. So we are going to take year 1.4, year 2.4, and year 3.4, okay? Once you have all these values there, you just have to take the average. So you are going to averaging the value of the gross seasonal coefficient for all the first quarters, the same for the values of the second quarters, the third and the fourth. So this value here will be your net seasonal coefficient. So you are going just to copy and paste this value in the column of the net seasonal coefficient, starting in this case from the first observation and up until in the last, that is the second quarter of year 4.
Martina, just a clarification. So
Yeah.
we copy this minus 60.79.
Yeah.
This number that we copy is the average?
Yes, it's just the average of the values of the gross seasonal coefficient.
Okay, because these values are missing, and that's why we, in how the moving average was calculated, these values are missing, and you want to recreate those values again.
Essentially, yes, we want to recreate those values also for the observation that were missing, because we are going to use them to compute our forecasted value. That's why we fill the whole column in this case.
Okay, and there's basically negative value means that it's lower, of course, and the positive value means it's the predicted is higher.
Yeah, in this case is seasonality. So negative values refers to period of decrease and positive values of increase in our time series. Okay, so essentially negative values are, for example, this part here of the seasonality, while positive value are this part here. Okay.
Yeah, excellent. I got it.
Okay, so then in order to realize our forecast, we then need to create a variable of time. This variable of time, you know, that should be always an integer value time, okay? This is the first condition we have seen in class regarding time series. So we start by 1. And just add 1 for each period of observation. So we are going to end up to 18, because remember, we are going to realize forecast for year 5, quarter 1 and 2. So we are going to include also these 2 new observations in our time variable. Okay. So the time variable.
Martina, how you can predict the future with this method? But please carry on. It's really exciting.
What? Sorry?
You're going to predict the future with this method. You can predict the future, right?
Yeah.
What is going to happen in year 5, even though we don't know that there's no data.
Exactly. We are going to apply this method to realize the future forecast value of sales of this company. And clearly, we are interested in particular in these 2 values that are the not observed one originally. Okay. Okay, so once we create our time variable, we need, and we are going to see why we need this, to compute the mean of the trend cycle that we got at the beginning and the mean of this variable time. And we are going to take the average of these 2 variables just for the observation, so the yellow ones that are those presenting the trend cycle component, okay? So to do that, you just click on average and select the observation for the trend cycle, and the same will be for the time variable. And we are going to use these two calculations in a while. So if you remember, when we apply an additive model, we are assuming that there is a linear relationship between our variable of interest, that would be estimates of sales, and time. So in order to do that, and I'm going to show the formula. So this is the linear relation we are going to assume, the linear trend, okay? We have observed this from the graph, okay? So you should be able to interpret the graph because it is fundamental to choose the appropriate model to be applied. In that case, we have a linear model. So we are going to apply additive model with linear trend. And the formula of the linear trend would be this one. If you remember, in this, which is actually a linear regression that we are going to realize step by step by hand, we should determine the value of alpha and beta. In statistics, the beta will be the covariance between x and time over the variance of time, while our alpha will be the difference between the mean of x minus the estimated value of beta times the mean of time. So that's why we need the mean of the trend cycle and the mean of time, because we are going to build these two parameters here, okay? So to do that, we should realize this series of computations. So we need to do the trend cycle minus its mean, and you just have to select the observation of the trend cycle minus the mean of the trend cycle we computed before. We put the dollars here because the mean of the trend cycle will be always the same. So we are going to fix this cell, okay? And so we are going to tell Excel, well, compute this difference, changing actually this observation as we proceed, and fixing the mean at this value here, that is the one we computed before, okay? So again, if you double click here, you will get the values for the whole column. The same should be realized for time. So we are going just to subtract time to its mean. Again, we are fixing the mean for the same reason seen before. So this cell will always be the same. So we are going to tell Excel, well, compute this difference for each observation, fixing the mean at this value here. Okay?
Yeah, I think it's great. I think it's called like absolute reference, where you like fix the cell, specific cell that you will refer with this dollar signs.
Yeah.
Yeah, great. We follow you.
Okay, so then we should compute the square value of the variable time minus its mean. So you just select the cell and put at the power of 2. This is quite easy. And then we need the product between the trend cycle minus its mean that we got here and t minus its mean that we got here. Okay? Why we need this? Because if we take then the sum of t minus its mean at the power of 2, we are going to get the variance of time. That, if you remember, is the denominator of our beta. While, sorry, I should put it away, no, okay. And then if we take the sum of this column there, that is the product between the trend cycle minus its mean and time minus its mean, we are getting the covariance. That will be, again, the numerator of our beta, okay? This part here. So once we get these two values, we are able to estimate our coefficient beta that will be used to create our linear trend equation that will be fundamental to realize our sales forecasts, okay? So The beta would be just the covariance over the variance. So just this value here over this value here. Okay? Once we have the beta,
Martina, just let me ask. So, what does beta is a coefficient, right? And this is coefficient of covariance.
Yeah.
By variance or covariance of x. Well, in this case,
sales,
and the variance of time. And what does this number 9.89 mean?
It actually tells you what is the relationship between sales and time. So it means that there is a positive relations between sales and time. It is the rate of change. So as time increases by 1 unit, sales are going to increase by 9.81.
So in this case, 1 unit is 1 year. So every year, on average, the sales are growing by 9.89.
Exactly. And this is going to be used to estimate this linear trend that will be used to realize our forecast in the next 2 steps. Okay. So once we get the beta, we can compute the alpha, that is actually the intercept of our linear trend equation. That, as we have seen in the slide, is just the difference between the mean of the trend cycle we have there minus the beta we computed before times the mean of time. Okay? So alpha will be the intercept in this regression that we have seen before, this one, okay, is the intercept. So why we need these two, the coefficient beta and the intercept? We need them because now we should compute our linear trend equation that will be the fundamental step to realize our forecast. So we are going, in this case, to fit this equation here. So we are going to take, let's say, an estimated value of the trend cycle, and these allow us to get the values also for the observation we originally lose, okay, but also for the other two we would like to forecast, okay? That's why we need these DC stars. And these DC stars will be just alpha, so the value we got before, that again is going to be fixed with dollars, plus beta, again, the value see before, fixed with the dollar, times our time variable, 1 in this case, starting from the first cell, okay? So this regression is going to be fitted for each observation, including also the last two related to year 5, quarter 1 and 2, that are the ones for which we want to forecast the value of sales. Okay, is that clear? So once we estimate this linear trend equation, this is going to be used to realize our forecasted value of sales. So our forecasted value of sales, these sales stars, will just be the trend cycle star, so the one we got just in the previous step, this one, plus the net seasonal coefficient. Okay, so this plus this will give us the forecasted value of sales. Okay, so
Martina, just let me maybe summarize in a way. Yeah. So we have this alpha and beta. Beta is a rate of change. Alpha is where we start. Actually, all these calculations, the intercept of the sales, and so we use the data from the TS, so the moving average, to predict it. And then, because we know the difference between the moving average and the real sales, in column L, we actually now can use this prediction of the moving average plus the deviation which we calculated before to predict the real sales. Exactly. Is that right?
Yeah. So we are, in this case, obtaining the forecasted value of sales, adjusting for seasonality. That's why we add the net seasonal coefficient. Okay.
Yes, clear.
Okay, so this will be just the sum of these two components and allow us to get the forecasted values, especially, and the two value of interest, that's why they are underlined in yellow, are the value of quarter 1 and 2 of year 5, okay? That were the initial question of this exercise. So the exercise actually asks you to realize the graph, fit a linear model, and realize and take the forecasted value of sales for year 5, quarter 1 and 2. So this will be the answer. So after realizing all this calculation, we get a value, a forecasted value of sales in quarter 1 of year 5 equal to 597, and in quarter 2 of year 5, 675. Okay? They can be $1 million or whatever. Okay? So these are the forecasts. But once we got the forecast, we should be able to evaluate the goodness of fit of all these calculations, so of our linear additive model. So to do that, we should compute the error term. So if you remember, the last step of this analysis means evaluate the goodness of fit. There are different measures that can be used to do that. The mean absolute error, the mean percentage error, and the most used one, and that is actually the one you were asked to compute in this exercise, is the mean absolute percentage error. So the first things to get this, which is actually just an average of the error, estimated error terms over the original value of sales. So we are going to compute this ratio here. So the first things to do is to compute the error term. The error term will be just the difference between the original values of sales minus the forecasted value of sales we got in column L. Okay, just a simple difference. You remember the formula we have seen before, we need the absolute value of this error term at the numerator. So you can easily compute this writing apps. In English would be apps.
So absolute value means we don't care if it's minus or plus. Actually,
exactly.
we want to have plus.
We don't care about the sign. Exactly. So to do that, we put the function apps. And we say,
and Martina, I think what is with this absolute value, it just tells you the deviation. It doesn't matter it's go below the predicted value.
Exactly.
What we really worry about, or we would really want to know, is how much the error varies around the real values.
Exactly. So we apply the function apps to the error cells, and we got the absolute value. And if you see, they are exactly the same of this column, but we are losing signs actually, because in this case, it doesn't matter whether they are positive or negative. Then we need to do what? The ratio between these absolute values and the original values of sales. If you remember the formula, you have the absolute value of the error term over xt, that is the original value of sales, in this case in column B. So we are going to divide the absolute value of the error term for the values in column B. And you should do that for each observation, okay? Once you got all this calculation, you just take the average of this column, and this will be your mean absolute percentage error. How we interpret this value? Whenever you have a value, and this is also what you have here, of mean absolute percentage error that is less or equal than the 5%, it means that our model has an excellent goodness of fit. So we do well when computing our forecasted value of sales in this case. So our forecasted values are reliable, okay? And this is the exercise.
So Martina, can I ask a quick question here on the mean absolute percentage error?
Yeah.
Is there any sort of following conclusion we can make? Let's say if we have an excellent fit, what does that suggest apart from that our values are well aligned with the model? Is there anything else we can conclude just for the purposes of the discussion of the assignment?
So you are going just to conclude saying that given that our model has an excellent goodness of fit, we can stay with this forecasted value of sales. So these values are reliable. So we can, let me say, be confident by the fact that sales in year 5, quarter 1 and 2 will be approximately equal to the value we got in this case.
Mm-hmm. Yeah, that makes sense. Okay, thank you.
Martina, the acceptable statistical error, if I'm correct, is 5%. Right? Whatever, if you have less than 5%, it's acceptable.
No. Yes,
error.
Exactly.
And if it's more than 5%, it's non-acceptable, means you
well, there are intermediate values. So
yeah.
if you have between 5 and 10, it is satisfying, not excellent. The worst thing you can have is a value greater than 10%. In this case,
so in this case, it's very clearly predicted because the pattern was possibly very consistent. And so we predicted with only 1% error maximum of the prediction.
Yeah.
And this Martin, the last thing from this where it's written the titolo del grafico, this the figure. So these two lines, what do they show? It's one is real sales and one is moving average or predicted?
No, these are the real sales, so just this one, and this is a line of tendency. I have just started using this option here. It can be added or not. It just helps you to identify whether the trend is linearly increasing or not.
You know what would be interesting to have these two lines? One is sales real and one is predicted, and just see how close. But I think in this small graph they will almost overlap fully because the size of the graph is quite small. So what I'm saying, if you take two columns, predicted and real sales, so my feeling is that they will be really close.
So if we plot sales and sales stars, are you saying?
Yeah, if we can make another graph, for example, yeah, sales and sales star, yeah.
Yeah, if you
just curious how it will look.
Yeah.
So we highlight both columns. And we do two lines. And here they are. They're almost identical. You can see only a little bit blue sometimes shows up, which means blue is the real value, and the orange is the series 2, which is predicted. And you can see it's perfect prediction, really.
And this is perfectly coherent with the value we get of the mean absolute percentage error.
We can possibly delete this graph not to confuse, but it's actually I wanted to do this exercise to demonstrate that how this, what does 1% mean? You know, perfect fit.
Okay.
Martina, do we have any questions from students at this point? Maybe not. Martina, do you think we have time for the second part, the second exercise?
Yeah, I think we can spend a few minutes.
Because I think that is quite quick, actually. I was able to do it quickly. Maybe we can do the same thing quickly going through the second one.
Yes, wait a moment that I'm going to share my screen again. Benchmarking, yes. Okay, so in the case of benchmarking, the main aim is that of comparing the performance of a company of interest that in the case of this exercise is alpha with that of the sector. We have seen in class that there are different ways in which the sector can be identified, and we are going to apply there all these definitions here. So essentially, in this exercise, you have 4 financial ratios for the company that are the current ratio, the return on investment, the leverage, and the elasticity of asset. We have discussed this financial ratio in class, but briefly, if you remember, current ratio is current assets over current liabilities, and essentially gives you information on whether the company is able to cover its current liabilities with its current assets. So a value approximately equal to 0.5, that is 50%, is good. Return on investment is net income on investment. It's one of the most used performance measure of the company. Unacceptable value is generally higher than 8%, but clearly it may depend on the kind of sector the companies belong to. However, as I told you in class, for a clear and full comment on the performance of the company, this index should be read together with the return on equity and the return on sales, for example. Then we have the leverage, which gives you information on the amount of debt the company is using to finance its asset actually. And in this case, there is not a benchmarking value to define whether it is optimal or not, but we can say that an optimal situation is when the return on investment is greater than the leverage. And this will imply that the company is able to, let's say, generate profits from the debt, okay? Then the last one is the elasticity of assets, that is current assets over total assets. It is a normalized index between 0 and 1. So the greater is near 1, the better is the situation, because it means that the company has a flexible asset structure. So having a high value of current assets means that the company is able to cover its debt, its expenditure, its obligation with its current assets. Okay, so value equal to 1 is good. Okay, so in this case, we
Martina, so these 4 indicators, actually the performance of the financial performance of the company, right? All these 4 indicators, they are typical financial performance indicators of a company.
Exactly.
Excellent, thanks.
Okay, so in this case, we have this company, and the company of interest is Alpha. Okay, so we want to compare the performance of Alpha with that of the sector. So we should realize some calculation to define which is the sector or group profile to which we are going to compare the value of Alpha. Okay, to do that, we should compute all this stuff here. So we are going to compute the minimum, the 25%, the median, the 75%, and the maximum that, as we have seen in class, are the quartiles. Okay, so to do that, we are going to use the function quartile, select the column, in this case, for the first financial ratio, that is the current ratio, and put the 0. The 0 just tells Excel to compute the minimum value, okay, of the specified column. And this should be done for each index, for each financial ratio. The computation will be always the same. Then we should get the 25%. The formula is exactly the same, but you are going to put no more 0 but 1. So the 25% is the value that left at the left side, the 25% of observation. Then we have the median, same function, but we put 2. And this value is the value that divides your series of value into equal parts. Then we have the 25%, same function, and we put 3. And then we have the maximum. Once we have all this stuff, we need also to compute the mean. the mean of all the financial ratios. So we click, so we write average in English. You select the column you are interested in, and you got the mean value for the current ratio, the ROI, the leva, and the elasticity of assets. Okay. Then we need
so to clarify, you look at the distribution of this indicator, right? A distribution, minimum, maximum, and then the quartile in the middle, 25, 75, and median, which is 50%, I would imagine.
Exactly, and then we also
and in this case, greater than one is current ratio. If it's greater than one, like current assets more than current liabilities, it's good.
Yeah.
Means the median, the 50% of the companies have 1.4, means they are, they're doing good. Their performances, their current ratio is in kind of good condition of half of the companies. But the other half is the less than one that possibly is not. They don't have all the assets to cover their liabilities. So in this case, we look at their, how the sample looks like, healthy, unhealthy, and what's the percentage of this sample is having the problems or actually outperforming or underperforming.
Exactly. Can you hear me?
Maybe we can go in skewness and kurtosis. I think it's pretty, the distribution is clear. I just kind of commented on why we need to look at the whole distribution.
Okay, so then we are going to compute skewness and kurtosis. The function will be skew in English, and that for kurtosis will be cart in English. And you just select the column you're interested in. Why we need these calculations? Because we should observe whether our financial ratio presents a normal distribution or not, okay? Because this will be crucial, and I'm going to show you what are the different graphical representation we may have, because it is crucial to decide which kind of measure we should use to define our sector or group profile. If you remember, we have seen that the skewness and the kurtosis essentially gives you information on the shape of your data. So we have seen that the most typical distribution used in statistics is the normal one, that is this one, which is symmetric. So it means that the mean and the median and also the mode occur in the same point, the central point, okay? Whenever you have a normal distribution, skewness is going to be equal to 0, okay? And if you observe here, we got values that are different from 0. So in this case, we have asymmetric distribution, so not normal, okay? The asymmetric distribution may be negatively skewed if the left tail is longer than the right tail, or positively skewed if it is the opposite, okay? Then we have the kurtosis, which refers to whether our distribution is flat or it has a peak, okay? So it refers to the shape in this sense. And in the case of a normal distribution, kurtosis is equal to 3. So if you see there, we have values that are very different from 3. So we can conclude that our financial ratio do not follow a normal distribution. Whenever this is the case, you are going to use to define your group profile the median. Okay? If it may happen, even if it's rare, you are going to find values of skewness and kurtosis that instead suggests the presence of a normal distribution. In that case, you are going to use the mean to define your group profile. Okay, this is not the case. We have values that are different of skewness and kurtosis that are very different from a normal distribution. So we are going to define the sector profile, or It's the same, the group profile as the median. So we just copy and paste here the firm profile, that is the firm we are interested in, that is alpha. We just copy and paste this row here. And we copy the group profile, that is the median. So these are going to be the values on the basis of which we are going to perform our univariate benchmarking analysis. So we are going to do that for computing the performance gap. That will be just the difference between alpha, so the firm profile, minus the group profile. Okay? So in this case, we get both positive and negative values. So what does it mean?
So Martina, the negative value would means in this case underperformance compared to the median, and the positive value means overperformance compared to the median.
Exactly. So in the specific case of each financial ratio, what does it mean? We have seen that the current ratio is good whenever is greater or equal than 0.5. So in this case, we have that alpha as a value that is 1.07 and the median is 1.4. So despite having a good current ratio by itself, when compared to the group profile, alpha is underperforming with respect to the group profile because we got a negative value. Okay? If we look at the return on investment, we have seen that the interpretation of these financial ratios should be realized. We're looking also at the return on equity and return on sales, but despite that, an acceptable value will be starting from 8%, so 0.08. In this case, we have that alpha has 0.07, which is, okay, slightly lower than 8%, so acceptable, let's say, while the median is 0.06. So we got a positive performance gap. What does it mean? It means that alpha, compared to the sector profile, will be one of the best performer in the sector in terms of return on investment. Okay? The same will apply to leverage because we got a positive value. So also in this case, alpha will be one of the best performer in the sector in terms of leverage. So it means that alpha is able to realize profits from the debt contracted, okay? And finally, looking at the elasticity of asset, we observe both for alpha and for the sector profile very bad performance, because remember, elasticity of assets is good whenever it is approximately near 1 or equal to 1. So both the two profiles are negative, but once we compute the performance gap, we say that alpha is underperforming with respect to the sector. So in conclusion, what is the main aim in this case? So benchmarking tells you, well, if you want to evaluate the performance of a company, you cannot look at the company by itself. You should compare it with a bench. This bench can be a sector profile. In this case, given that our data are not normal, we are using to define the group or sector profile, the median. When comparing alpha with the sector profile, we see that it is underperforming in the case of current ratio and elasticity of asset with respect to the rest of the sector, while it is one of the best performer in the sector if we look at the return on investment and on leverage. So overall, alpha has good economic performance looking at return on investment and leverage, but has a poor liquidity performance. Liquidity, if we look at elasticity of asset and current ratio. Okay, this will be the conclusion of this analysis.
Martina, I have a question.
Yes.
So you looked at the difference between the real value of company alpha and the median values, of course, also real median values of the sample.
Yes.
You used the difference between the median because you found out the skewness and kurtosis, that it was quite asymmetric and not normally distributed.
Exactly.
Let's say if it was normally distributed, would you look at the
In
mean
that case, as
rather than median?
In this case, as I said before, we will stay with the mean. So to define the group profile, if the distribution of our financial ratio is normal, we are going to use the mean instead of the median.
But because it's not normal, and how we looked from kurtosis, because it was different from 3, which is the benchmark value, then we decided to use the mean deviation from the mean to understand our.
Yes, because both the kurtosis is different than 3 and the skewness is different than 0. That's why we use the median, because these two values, skewness and kurtosis, suggest that the distribution is not normal. So the synthetic measure to define the group profile, the sector profile that should be used is the median in this case.
Thank you very much. Indeed, I think I found it very
clear. I hope it is clear now.
Yeah. Do we have any questions by any chance on this?
Yeah, Max, I have one. Just for the purpose of the assignment, I just wanted to ask, do we need to demonstrate the distribution in a graph in the assignment?
No, you don't need it, because skewness and kurtosis are already a perfect synthesis of your distribution, so you don't need a graph.
You can visualize it if you want so, but it's from the numbers we can see the sample.
Okay, cool. Thank you.
All right, I stop recording then.